Yep. Okay, welcome to our last Wednesday seminar of the semester. It's impromptu. I'm given the honor to introduce my friend and colleague Tim Schmit for our discussion today. I was thinking about it as I'm looking at this picture. This is going to diverge a little bit, Tim. I hope you don't have 50 full minutes for us. But one of the difficult things about being a human being is that every once in a while you need to take a step back and look at yourself. We don't have an easy way of doing that. But on Earth, thinking about our weather and climate, in the last 50 or so years, we have discovered a way to do that. And there are certain people in our community who have exploited that discovery to its fullest. One of them is Tim Schmit. And here's what I mean about taking a perspective outside of ourselves. We can't make sense of everything around us until and unless we see things from a distance. And I think seeing things from a distance, observing them, actually making sense of what those observations mean from those remote platforms has been absolutely invaluable. All of us in this room have lived through a revolution, and it's been a silent one. 50 years ago, there was no way to have any faith in a two-day forecast. Absolutely none. No matter what time of year, where you were in the world, it didn't make any difference. Now, you should have reasonable confidence in 7 to 10 days, almost everywhere on Earth, at any time of the year. That's remarkable. Most of that revolution's been accomplished by the extraordinary amount of observations that we now take from space. People like Tim Schmit, who is an AMS fellow, and he won the Service to America Award from NOAA. These are high-profile awards, is somebody who's led that revolution for us. And we've been lucky enough to work with him, I have, for 30-plus years in this building, and to know him for that long as a person, in addition to that. Any of you who have been equally fortunate will realize this is such a quality individual that we're talking about. It's a real honor to be up here and be able to introduce him to you. I'm sure I haven't done enough, but Tim, I want you to tell us about the 50 years of revolution you've led here. Thank you.
Yeah, thank you very much. One point, I was a finalist for the Samuel Service to America Awards. They call it the Oscars of government service. So I didn't actually win it, but 1 out of 7, that's pretty good. So.
You won it.
Anyway, so Tim Schmit, I work for NOAA, National Oceanographic and Atmospheric Administration, but I work down on the second floor. So best of both worlds. I'd like to thank my co-authors and about a lot of 1,000 other people that weren't listed there. So I'll start with my beginning. My dad did research with infrared detectors growing the crystals. And so growing up, I thought everybody's dad talked about phase concentration and building crystals and the joys of the infrared. Apparently that's not the case. But anyways, I was 13 years old, did an aptitude test, and it said meteorologist. And I said, well, maybe someday I could get a master's degree in meteorology from the University of Wisconsin-Madison. Boom, that's what happened. So this might be the most important slide because this has my email on this, but as of January 1st, don't try this one for NOAA anymore. So either of those other two should work. So a lot of acronyms, but there's one goes, Geostationary Operational Environmental Satellite. Geostationary talks about the orbit. So let's say this is the Earth here. We've got polar orbiters that go around the poles, and they're good because they give you the whole Earth and all that good stuff. But then we have geostationary, they're much further away, but then they rotate at the same rate as the Earth, so we can continue to look down, get high resolution rapid imagery. Note, this wasn't exactly to scale, so just anyway, so every outline needs every good talk needs an outline. So here's my outline: past, present, and a future. So let's go way back. So when then meteorology department was started, it was over in Science Hall. Professor named Verner Suomi and engineering professor Robert Parent. They were working with NASA to do the first measurements of the Earth of getting, for example, the infrared radiation or the heat of the Earth to estimate the heat budget, how much energy is going in and coming out of our Earth. So that was 1959. I mean, as you know, that before that, satellites really just beeped, okay? But this was the first satellite in space remote sensing. So every other image you see can trace back to Explorer 7 with PIs here on campus, University of Wisconsin-Madison. So you'll see this chart a number of times. If you get lost, decades along the bottom there. But we're going to do something what we probably shouldn't do, and we're going to put 90 years of remote sensing satellite data into 42 minutes. So recall we have operational, so the work I work for is a satellite group in NOAA, and it operates these two satellites, an east and a west. And you can see the coverage there. The west coverage covers the Pacific here, the east covers that, and there's also a ring of other satellites operated by other international partners around the globe. So, we get data really wherever you are around the globe from one of these. This happens to be, again, a color-coded infrared image showing the heat. So, for example, blue and white are colder clouds versus the red, warm land or ocean. So before we had operational GOES, we had experimental satellites, and these were operated by NASA satellites. And they had, for example, the first one had one visible band. So here's the part of the electromagnetic spectrum, the visible band, you can see, and it had this one visible band. So this shows what the instrument measured of, so one visible band in this satellite that was launched in 1966. And who was the PI of the instrument? That's right, Verner Suomi, meteorology professor here. So this December 11th, oh, that sounds like an interesting day. December 11th, okay, that's right. Anniversary today of the first images back from space. So it was launched on December 6th, December 11th, first images. And you can see now, we can see a time series as we look down on the Earth, as in this case, the sun comes up, illuminates the full disk, and gets darker again. But again, so every time you see a satellite that loops, again, you can be traced back December 11th, University of Wisconsin. Recently, the University of Wisconsin SSEC here digitized some of these old pictures here. You can see the little hole punches up here. So again, here's another image from December 11th. This happens to be from 1974. So again, not too bad, 50 years ago. And I don't know if you noticed, but yes, those are my hands. Anyways, but we didn't rest. 66 now launched in 67. Now not just one spectral band, but 3 spectral bands in the visible. So now we could do things and look like this nice color image because you had a red, green, and blue component. Everybody talks about seeing the, we've never seen the Earth before from space without map lines in the Apollo program. Well, that's good and nice, but that was after this. So obviously not enough people were reading the Bulletin of the American Meteorological Society in February of 1968. So this is also before the internet, so it's hard to get that up. There are other experimental satellites before the GOES, but now we added, so here's another part of the electromagnetic spectrum. This is the infrared part. So we can see we added one band in the infrared window, again, to get the heat. So now we can see where clouds are during the night as well during the day. So here's an example. This happens to be Mount St. Helens here exploding, so the visible on the left and the infrared on the right. And so you can see this the shadow and the cloud, and of course you can also see in the infrared the cooling of that cloud. So again, this is some of the first images. This was experimental, but again, this is the precursor to the GOES. That was so successful, I said, well, we got to turn this in and make it operational. I mean, it's there all the time, got to work. GOES. So now we start with GOES 1. To help confuse people, we give them letters when they're on the ground, and then they earn their numbers when they get up to this special geostationary orbit. So we launched GOES-A in 1975, October, and then when it got to orbit, geostationary, then it became GOES 1. So again, we're coming up on the 50th anniversary of GOES 1. Launch pad 17A, but that's kind of a detail. So again, we had this one visible band, and we had one IR, similar to the precursors. Here's an example of GOES 1, just a visible image showing a tropical cyclone. Yes, that is India you're looking at, as the satellite was moved over that part of the world for a global experiment called GARP in 1979. So that's GOES 1. Here's another example, again, with the visible, which is great during the day, but it's reflected light, so it goes to dark there as the sun sets, as we're not illuminated. But yeah, on the right there, you can see the infrared. I should say all these images that were made here was using software developed in this building and data that's stored in this building. May 18th, 1980, Mount St. Helens. Not the best data sometimes, but if you look right here, you can see the stratus, boom, the cloud, the thickening of the stratus around it as the ash plume moves to the east. Maybe it's even more obvious to look at the rapid cooling here in the infrared as the ash plume goes towards the east. So there's a GOES 3 example. In general, when we bind these, we're buying 3 or 4 in a series, just to keep the cost down a little bit. So then after the 1, 2, 3 series, now we're GOES 4 through 7. And what we added was some vertical profiling of the atmosphere and improved spatial resolution of the field of view of what you can resolve on the ground. Still one visible band, but now a lot more bands in the infrared. So this red is an Earth-emitted spectra. So if you read on, so this would, we call it a window region, or you're seeing the surface, but here you're seeing higher in the atmosphere due to absorption. So, but normally we would basically get the 1 infrared window and then 2 of these other bands. So then we're up to 4 bands now with routinely with GOES 4. Our friends in Europe had added a water vapor band in the late 70s, 1977 on one of their geostationary satellites, where we caught up to them here in 1980 with now this water vapor on the GOES 4 series. And again, we also had some other ones to do vertical profiling. So here's an example, Hurricane Norman. Again, you can see there's some stripes in the images, so it's not as good quality as we say today. We're getting data, for example, every half an hour routinely, which is way more than, again, those polar orbiters, because they're often on the other side of the Earth. And again, revolutionary at the time, but as you'll see, we'll have more improvements over time. So I mentioned we have this water vapor band, and so now you can see the mid part of the atmosphere, and these swirls show you the upper level motion of the cloud. The darker colors are drier air, so you can see this big low off the East Coast, obviously where it is, and you can see how the dry air is wrapping in. Again, it's a little bit noisy, it's a little bit striped, but again, pretty impressive. Again, this happens to be from 1982. For, again, this GOES 5. GOES 6, Hurricane Raymond. So this is a category 4 in the Eastern Pacific there. So again, before satellites, you maybe had a couple ships, maybe you didn't. If you looked at the climatology of satellites worldwide, anytime there was a new geostationary satellite put there, the number of hurricanes went up. They didn't really go up. You could just now see them from this rapid scan that we got from our geostationary perspective. So that's GOES 6 in 1983. So GOES 7, here's again an infrared loop. So now the colors are the coldest. And this is Hurricane Andrew. Very famous. It first made landfall just north of Miami there, Homestead, Florida. Weakened a little bit, strengthened again, and then made landfall in Louisiana there. So a cat is either upper 4 or lower 5 when it made landfall in Florida, and then higher in Louisiana. GOES 7 was unique insofar as, actually, go to the next one. So if you look at any time, you could draw a vertical line and see how many satellites we had up there. Well, if you notice, about these 5 years after GOES 6 had an encoder bulb issue, but before we launched GOES 8, we only had 1 satellite up there. As I showed earlier, we were supposed to have 2 satellites, and ideally we have a backup one. Well, like I say, due to a number of reasons, there was an earlier launch failure. So here we just had 1 satellite, but it hung on. So, but for 5 years, then we'd shifted to the east to look at hurricanes, and the west for severe storms coming in the winter. But again, so GOES 7 was hung on until what was launched was GOES 8. I was hired in 1987 to get ready for this, well, GOES I, which was going to become GOES 8 because we were going to launch in 1988. We didn't. We launched in 1994, as you can see there, but luckily GOES 7 hung on. And GOES 8 was another step up. Not necessarily, we still had the 1 visible, but now we had 4 infrared bands. So 2 in the window, so you get the surface. 1 of those is water vapor to look at upper level moisture, and then 1 for that's very sensitive to temperature, so be it fires, fog, etc. So that was a big step up. I mean, just looking at this, again, GOES 8, here at Blizzard in the Midwest, again, you can see the, the low spinning up, the warm air, the conveyor belt, the cold air from north. But again, just how much cleaner this signal is than the previous generation of water vapor that had the stripes and the lower signal to noise, so some of that blocking. So there was GOES 8. GOES 9, after it was done with its operational service here, Japan had a need for a satellite. So this was moved over to Japan, and for a number of years operated there. So again, you can see just the number of typhoons and super typhoons, very active season here. You can also see how the Earth is bouncing a little bit. It's a high inclination. That's one of the reasons why it wasn't an operational satellite for us anymore. But again, was able to help fill in this global constellation. So not surprised by the location or intensification of tropical cyclones around the world. I guess my favorite example with GOES 10, now this is actually on the left is a band difference between 2 of the bands, and on the right, again, you can see that it is a visible or a reflected light. So nighttime, 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 and then you can see here, and you can see that plume there. What's that plume from? That plume's from a volcano in Ecuador. Why do we care about volcanic plumes in the atmosphere? Apparently engines stop when they run into these plumes, and apparently pilots don't like that. Insurance companies don't like it. People flying on it don't like it. And truly, satellites are the king for being able to monitor this, because they're always looking down. They have the spectral resolution, their algorithms to say, avoid that area due to volcanic ash. There's a visible band off the west coast of the United States, and you can see what they were called ship tracks, but they're basically a stratus deck, and then you have a ship goes, and the matter from that interacts with the cloud, and then maybe glaciates. So then then they get blown around by the wind. But again, you can get an idea at least where the ship was by looking at these visible images. You can also see it in some of the other infrared bands as well. It's easy to pick what GOES 12 famous loop would be. Hurricane Katrina, which of course became a Cat 4. Everybody forgets it. It crossed over Florida first. And some people, but it's only a Cat 1. Well, it's still a hurricane. It's still a hurricane. And you can see it intensifies. But if you just look at the the size of that. And of course, you can have the best forecast in the world, but often when people are going to take action, they really need at least two pieces of information to and so one of the things what the GOES can do, you know, you get their forecast is always going to hit, but then people look at this and see how big is that, how it's expanding, put scary color enhancements on it. People, okay, it's time to get out. So again, Cat 5, Hurricane Katrina. So as I mentioned, we had a number of, so we've still had this one visible band. Again, we have this shortwave band. That's good for fires and fog detection monitoring. Water vapor, again, mid-level, and then two infrared bands. So you can see how these spacecraft look very different between the GOES 8 through 12 and 13 through 15, and the spacecraft were very different. Larger batteries. Sometimes during the year, the spacecraft is eclipsed by the Earth, so it doesn't get solar powered. So in the earlier satellites, we just wouldn't take data then. And then we realized that weather still happened even if we didn't monitor it. Hence bigger batteries on the GOES 13 through 15 series. But again, very similar of the spectral coverage. So slight difference, shifting one band over. But again, we went from 4 infrared bands and 1 visible to 4 infrared bands and 1 visible. So again, that was really kind of a continuity for this GOES 13. GOES 13, my favorite loop here is Hurricane Matthew. And you might think, well, this isn't like a really amazing hurricane. What could be so unique about this? But Tim got up early in the morning to look at this loop. Well, this is 2016, and GOES-R, the spacecraft, was sitting here down at Cape Canaveral. Okay? So don't worry, because the forecast was that the hurricane would go just off the east. The worst, strongest are going to be in that forward, on the right-hand side. So everything should be okay. But again, going like this versus like that could be a very different situation. So very happy when that stayed off, everything was safe, and then we were able to launch just that fall. So GOES 14 is this is Hurricane or Superstorm Sandy. So we knew we were going to get this 1-minute data on a new generation satellite. So some of us said, hey, can we practice with this GOES 14 that's up there in space as one of our backup satellites? To my amazement, they said yes. So I learned later that the person who made that decision, she was retiring 1 month later. So anyway, so get people at the right time is the trick there. So I guess I got to be the one that said, where are we going to look each day? Well, we had done earlier things. Early in the month, this was going to go back in storage. A colleague says there's going to be an epic storm. You guys got to leave it on. Well, I asked them, can we leave it on? They said, sure. I gave them the coordinates. I was very nervous that I was going to give them the southern hemisphere coordinates and we're going to miss this unique 1-minute data, but we got this good data set. And again, so now we would have this 1-minute data, which we did in parts of 2012, 13, 14, and 15 to prepare for that next generation. So again, the circulations, the convection, the vertical wind shear, all can be seen there. I mentioned we have this 3.9. So this is showing the hot pixels, and they're hot for showing, for example, where the fires are in Southern California. So during the night, we're just showing hot pixels, and during the day, we're showing that and the visible. So you can obviously see the smoke there during the day. It goes a little bit fast. So as I tried to explain to someone when I said, we take our satellite, we look at these, fires, and see how they change sometimes every 1 minute from space. I said, wait, let me stop you right there. Do you mean to say that we look at fires from a sensor that's the 10th way to the moon? That's exactly what I mean to say. And then, of course, they're quantitative products as well. After GO 13, done with its operational service, it's now, it was moved to over the Indian Ocean to support the U.S. Space Force and some of their weather. And now they also have using GOES 15 as well. So again, a lot of global coverage. But now we get to the GOES R series, which became GOES 16, which, as I said many times, everything's going to be better, better, better. So more spectral bands, finer spatial resolution, and more rapid imagery. We went from doing a full disk image, let's say every 3 hours, to doing it every 10 or 15 minutes. And we'd have these mesoscale or rapid scan, that's what you can see on the right there, as often as every 30 seconds. Not over the whole globe, but just at regions of fast turned interest. I had a boss once, and he always used to say, well, yeah, but what did you do, Tim? So here's an example of one of the things I did. So even before launch, so this, you don't have to understand it, but this is a time chart of what the instrument was going to scan. So it's going to interleave scanning this full disk, also taking some scans of the continents of the United States, and also doing these mesoscale images. So that's fine, this is what the requirement said. But you can see there's this gray area where I like to say the instrument was up there to twiddle its thumbs and just wait. So I worked with the engineer and said, well, you know, could we fill that in? Now this is only over 10 minutes, but now we went from a full disk every 15 to every 10 minutes. I said we suggested that in 2014, and it got done right away in mid-2019. But that's the operational for all the ones. So I should also, so again, GOES R, now we don't just have one visible band, we have two visible bands, and we have what are called these near-infrared bands. They're also reflective bands. We don't have 4 bands in the infrared, but now we have 10 bands in the infrared. So I started working on this ABI in 1999 when it was going to launch in 2008. Probably heard, launch in 2016, but okay. But it was going to have 8 spectral bands. Was able to control the powers to be that we needed 16 spectral bands. That's kind of now become the international standard for looking at for these advanced imagers around the world. Proud to say a lot of the band champions, of course, have UW connections, be it Verner, Suomi, the father of satellite meteorology, but a lot of other names as well. So again, we were able to show that we needed this data, and it got on. How to become a band champion? Apparently you write a memo in 1989 that says, let's put this spectral band on, because it'll be good for looking at dust and cirrus and cloud phase at night. Don't worry, we got it done. Memo in 1989, got up in space in 2016. So anyway, sometimes it can go slow, but in the meantime, we use computers to simulate what kind of data that we would get. So here's a simulation computer model of what Hurricane Katrina would look like. So again, we could use that to run through the system to practice our level 2 products on, visualization, etc. So as I mentioned, we got to have 2 visible bands, 4 infrared bands, or I think of them as near visible bands, and now 10 infrared bands. So we can see a lot more of the atmosphere. So one of the things I really enjoy about my job is when we get the first data. So this is some of this first light data from GOES 16. So again, after 17 years, here's the data. Here's the individual spectral bands that we have on them, and then some combinations. So these are red, green, blue. We take some of those 3 or more spectral bands and put them in different components and combine them. And you do that so you can have different looking phenomena kind of pop out. So again, be it if you're interested in where the snow is, or is a cloud glaciated on ice phase, or where a rocket plume might be, these are all different combinations of red, green, blue. So volcanic ash, air mass, cloud distinction, convection, day microphysics, day snow cloud, dust, fog, natural color plume, and a true color one. So again, there's some examples, some early GO 16 data. I can't just show one GO 16 loop. Here's some meso data, which is every 1 minute, showing the shadow of the eclipse following it as the shadow moved up. So again, you can put research requests in for this, some of this, where you want this 1 minute data. There are all the operational uses, and then there's research down at the end, which I get it. But anyway, so we're able to stitch this together. This is one of these bands where the surface is very bright, so there's more contrast. That's the whole game in remote sensing. Contrast spectrally, spatially, or temporally. Here's just another example, taking one of those on time compositing in 2017 and 2024. So you probably read like, oh, the duration's going to be longer, this time than last time. Well, this confirms it. Yes, it was. You can see how the shadow size was bigger in 2024 because the moon was relatively a bit closer. GO 17. So this is the Western Pacific, and you can see, if you look right here, this is a water vapor image, but it's differenced in time. So there was a big volcanic tongo went off here, and then you can see as that energy went, watch here, it goes straight up, and then it's the top of and then kind of goes out, and you can see that leading edge. We could track that a number of times when they intersected on the other side of the globe, and then energy came back around. So anyways, that's kind of a mind-bending what you're looking at, but anyways, GO 17. I showed a loop before about fire detection, showing hot spots and smoke, but you can see how much better this GOES-R is. Really, this GO 16 series, 100 times better, so it's finer spatial resolution, but now we're getting data, for example, every 5 minutes, not every 30 minutes, and again, we have more spectral bands as well. So again, it's not just to look at the images too. You can make a derived product from this, and then that can be used to put in a model, for example, say where the smoke's going to go, or etc. So in June, we launched GOES-U, which became GOES 19 then, and again, we were able to get some of the first data. So that's why it has a preliminary non-operational. So don't use this for anything official. This is preliminary non-operational. So we compare it, again, these are the 16 bands, compare it to GO 16, and you flip back and forth, and yeah, you see some little differences, but by and large, you know that 19 is working pretty well because it looks very similar to 16, our current operational satellite. So then, again, we're currently in the post-launch checkout before GOES 19 goes operational this spring. So this Hurricane Milton, and again, 30-second imagery. Let's go on. Here's another RGB, the ASH RGB, using 4 different spectral bands, and you can see here, just west of Mexico City, you can see the plumes of the ash there. And let's see, where's James? The volcano is called? Yeah, see, that's what I said. I was afraid to say that. Anyways, but again, aviation uses for this, because again, people don't like to fly there. As I mentioned, we've got all these images, and they're great and wonderful to look at the images, but then we can also use that to make derived products. So not just your eye looks at that and says, oh, there's a cloud, but you teach the computer to say there's a cloud there and how high it is, or you track them over time and you get an idea of the wind field, or rain rate, total, how much moisture is in the atmosphere, the instability of the atmosphere, etc. I should also mention there are other sensors as well on the spacecraft. For this GO 16, there's a total lightning mapper, or GLM. There's also space weather instruments. for the space. So again, and we're always doing the research to get into operations for these new, and this is just a subset of those original products. So space science also brings in via the antenna this SUVI, solar UV imager. It's got 6 spectral bands. And again, if you just look here in the center here, you see a big, you don't have to understand it all, but wait for it, boom. And that was Earth-directed pulse, coronal mass ejection, and that's what gave us, a couple of days later, Northern Lights in October. So again, from this satellite, we're not just looking at the Earth, measuring what's happening at the spacecraft, but also looking out at the sun. So, you know, I mostly talked about the imager, that we went from the first of its kind to the first operational to orders of magnitude improvement. There's a whole other instrument of vertical soundings. We had the first of its kind in 1980, first operational in 1994, and we're still waiting for the orders of magnitude improvement, which will come on our next generation satellite series. So again, even though we always have to plan ahead. So this one will also have the east and west, but also have a satellite in the center of the country, and it'll have this hyperspectral sounder that I'm very excited about. So the imager will be slightly improved. It's, for example, got 2 new spectral bands at 0.91, another near IR band, and a new water vapor band that sees lower in the atmosphere at 5.15. But again, the big improvements is going to be at this sounder. So if you look at that green curve, they're now, instead of getting, for example, 11 pieces of information that we'll get from the imager, which averages, we get 2,500 different spectral bands from the sounder that gives us more vertical resolution. So we had a legacy sounder, and that's what I would say is in that blue box. But this next generation will be much improved. We'll go from the blue to the green, which I argue is even a bigger improvement than when we went from our legacy imager to this advanced baseline imager on the GO16 series. And this sound will give you more information about moisture and temperature and winds. And there were, again, computer simulations run and shown for over the continental U.S. Estimate that this new sensor be the most important with all the other observing systems that we currently have. I'm not really going to talk about trace gases, but with this sensor we also have the capability to do a number of those as well. So if you look at this one point in Wyoming, and then on the right is basically the temperature and moisture profile, temperature in red, moisture. So you can see it's low down, it's moist, and then it rapidly dries. But you can also see in this profile here, here's the surface, and it's warming with height here. And that's great if you know what the atmosphere here is, but you also can look at the spectra, and that's what these high-resolution sounders are looking at. And you can now, of course, do it in time. This is, of course, simulation. But just by looking at that spectra, you can get the idea of how the inversion is growing and decaying. Of course, that's related to severe weather and instability, etc. So again, we really don't have this capability yet. And again, just as we have a ring of imagers, today the world is building out this ring of advanced sounders. So China has one up there now. UW-Madison will have one up. The Europeans will have one soon, 2025. Japan has plans this century still. And again, in the center, this GXX, the sounder, we're looking at 2035 for that. So this is probably the second most important slide, because it's all boiled down in one slide. Everything I've just said, either the early ATS, NASA, or SMS, all the way through what we have today, the GO16 plus column, and then you can see the improvements that we'll have with the next generation that will be coming in 2032. So even finer spatial resolution. For example, that visible band we'll see 250 meter resolution. That's the box size of what we can resolve, which is pretty impressive. Like I say, a tenth of the way to the moon. We'll also have some finer resolution in some of the infrared bands. But you can see over the course of my career, if you look at, for example, with water vapor band, this is what I started with: 14 kilometers, 8 kilometers, 4 kilometers, 2 kilometers, next generation 1 kilometer. And pictorially, if your job is to tell the aircrafts where to not fly because of the turbulence, you want to use this? Nope, that won't make it. A little bit. This is where we're at today, and there are products that use today's imagers and looking at the ripples in the atmosphere will for atmospheric turbulence. But again, they'll be improved yet on the next generation. I contend that there's no other satellite series that I guess has done so much for so long, for so many, but it really all started here, measuring the radiation from the Earth from Explorer 7 in '59, or the first ATS spin scan cloud cover camera in 1966. And again, there's a lot of things that we measure, like I say, from the surface of the Earth, the atmosphere, etc. So this webpage has got just a link of a lot of other links, be it satellite imagery, data, calibration, software. Here's an RGB image, but of the sun, combining some of those spectral bands. There's also a number of web apps or different teaching apps. This tells you about parallax, but maybe the most fun is the spectral "What's This?" to teach about spectral resolution and pixels and all that stuff. So here's the pantheon of goes 1 through 19. Remember 19, preliminary, non-operational. And this is what I've been able to be part of. So anyway, I've been very honored to be able to help get ready for satellites and check them out and use satellite data, and even the early ones as well. Here's now throwing in that early ATS and SMS for the US GOES imagers. So I'll leave it there. I'll take any questions, and somewhere between 90 and 100 years, depends on how long GeoXO lasts, and a little over 42 minutes. So thank you. Any questions? Yeah, Bill, let's go.
Tornadoes, has an application for that?
Yep, okay, so the question was,
Part of it?
yep, do we use this for tornadoes? So we can't see the tornado per se, but we can see the clouds that are forming and how quickly they're forming. There's a product called Prob Severe, and it basically looks at how rapidly the cloud is cooling and has it switched from like a water cloud, a liquid water cloud, to an ice cloud. And so that can tell you, like, hey, there are two cells that look similar, but this is the one that you want to look at. It gives you a probability of, but they have a probability of severe weather in general, but they also have a probability of tornado or probability of hail, etc. So the other thing is, in general, there's good radar coverage in the United States, but radars go down. There's also not radars everywhere in the world. So satellite is definitely used in conjunction, because you can see these signatures in the satellite before you get a big signal from the radar. So tornadoes, directly looking at them, no, but inferring the cloud formation that causes them, yes. Liv?
The early GOES satellites that aren't operational anymore, are they still floating around?
Are they still floating around? Great question. So if you want to press your friends, you can say, oh, I think those are in a super geosynchronous orbit. Or, but after they fall asleep, then you can say, no, they're in the graveyard orbit. So again, there was that special, place where all your geostationary satellites want to be. They basically put them like 200 kilometers higher. So now they don't exactly follow the Earth, but they've made space so other ones can be there. And there's things on the internet that you can go and track it. If we were interested in where these early GOES are today, you can go look at them. But yeah, they're all still up. The lower Earth ones, they're gonna basically the drag of the atmosphere and over time degrade and come down and hopefully totally burn up in the atmosphere. But the geostationary ones are basically all up there.
There's a question online from Mary Patterson. What was learned from the solar eclipse data? Specifically, was there a temperature differential?
Yep. So, yeah, there definitely was a temperature differential. We were able to track that on one of the products is called the land skin temperature. And so you could definitely see that, how it's in general going down, and then went down a lot when the came over. You could also see how the cloud pattern, I know, both eclipses I've seen is like, oh, it's kind of cloudy. Well, again, you get less radiation that doesn't warm the surface as much. You don't get as much cloud. It clears out, and then the clouds can come back. And there's also a lot more research going on with that, as you see, especially with the recent one. Jack?
So one of the observations that I saw from your doctrine that really stood out to me was, when the satellites were viewing hurricanes, like as much as it seemed like there were suddenly more hurricanes happening, across the globe, especially in like the tropical areas, like the real discovery was that thanks to satellite imagery, we were becoming made more aware of that. And I think that's an interesting metaphor for a lot of phenomenon like what's like, as much as it seems like more of this thing we're observing is happening, what's really increasing is our awareness of it. And I wonder what were some other discoveries like that you guys encountered, like with the satellite imagery into your research?
Well, yeah, I mentioned how the satellites are king for looking at some of these volcanic eruptions, especially the ones. I was at a meeting with a colleague, and his phone goes off, and he turns to me and he says, "You and I are the only two people in the world that know that volcano went off." Right? Because in the middle of the Pacific, it went over, it went over. Looked at the spectral things, his phone rang, it was before it was operational. So there are things like that, just really amazing. I don't want to put anybody on the spot, but is there any question from someone who's a meteorology major, okay, or is taking a meteorology class right now, okay? Or from question from anybody?
Yeah, I'll ask
John, okay.
Nobody's got a crystal ball, Tim. Maybe you do, but I'm not aware of it. What do you think the impact of the new administration may be on the future of the GOES program? Now, I ask that knowing that there's been a lot of ups and downs in the last 50 years, but are people concerned?
Yeah. So what I showed you was our current plan, which I think is a good plan. I know I've talked to people who talk to people, and as you know, weather's really got good support on both sides of the aisle. How that exactly is going to fall out, yes, I don't know. I do know for some of these things, like I say, I showed you that ring of advanced satellites or whatever. Well, if we don't put our advanced sounder there, there's a big hole around the world for helping that measurement, and that hurts us more than anyone else. So, is there concern? Yes. We've got, and we've had, again, this nice continuous observation from GOES going back from 1975. So I'm confident that we'll keep, what we have today in, adding some of these new things. I think is a little bit further reach. Stay tuned.
Okay, thanks.
Yeah, one more slide.
I'll ask a question.
Oh, okay.
I really like the solar pictures. Can you tell me who named that instrument?
Yes, there is an instrument called SUVI, Solar UV Image. That's right, I came up with that one. But only they were doing a contest, and the old one was an X-ray part of the region, so that was SXI, Solar X-ray Imager. So they said, be creative, we're going to have a naming contest. So I gave them 10 wonderful creative ideas, including the GOES UV Cosmic Array, spelled out Gurkha, because I happen to know Jim Gurkha was on the committee to select the name. But I put one just dumb, what's the most simple thing I can think of? Well, I could take the X out and put a UV. SUV, SUV, congratulations, you've won, name the solar instrument. So I've had a lot of highlights in my career, and I just came up with this one slide here, showing me trying to explain how big the satellite is. Here's the space array, and the instrument would be up there. I have to say, as a meteorologist, when you're on a show called The Weather Geeks, I mean, it can't go anything more than that. And of course, there's a highlight every day right there. So, anyways. But yeah, that was the Sammy Awards or whatever. All right. The other thing, there are some posters up here and some swag for if you're in the room, so that's a benefit for showing up and not watching online there. Unless there's any one last question. Go on.
What is the significance, slide 2, the background matches your tie?
Yeah.
What is the...
Yeah, so they're very good that there is significance. That is a zoom up of a infrared detector. Do you want the surface to be super flat? And that was showing just the jaggedness or whatever of blown up. I don't know if it's 1,000 times or whatever, but yeah, I got that from my dad. So that was a picture of a mercury cadmium telluride crystal, probably in the early 70s or whatever. But yes. Yes, nothing random here. This is all there. I know somebody's asking like what's the deal with this tie? It goes 17 Hurricane Michael day cloud phase RGB. So anyway, who knew there was a place that you could give them an image and your credit card and they would make you a tie.
Does that all fit on the label on the back?
Yeah, that's right. So, all right. Well, I thank you for your time.
Thank you.